Last time I gave some intuition of Dijkstra as like a water flowing through the network. There's going to be like another physical interpretation of things, and I think this might be even better. So you should maybe imagine that you have, let's say for now, undirected graph, okay? So that the physical intuition works. So you have undirected graph, G, and think of vertices as a ball, like a tiny ball of a point. And each edge is like a elastic, like a stretchable string that connect two balls together. Okay, so you can stretch it. And think of this picture where you put you fix the source node S at position 0, and like there are going down is 1, 2, 3, 4, and so on. Okay, and then you fix every other node at somewhere far away, like infinite. So right now, every edge is really stretched. Okay, and now think that suppose you now just unfix every node, every other node here. Okay, meaning that every stretched edge is now relaxed. Okay, and then you let the gravity pull vertices naturally. Okay, so what will happen? Now this guy will kind of go up, right? It was stretched. It will go up, and so it might look like this. So if I ask you, once you let every string kind of stretch itself naturally, you don't fix anything. What are the position of every other nodes here? Well, it's going to be exactly what?
Whatever its length is, length of, so the distance from the source node.
Yeah, it's going to be exactly the distance from the source, right? A here, now it kind of hang around from S here. B is hang around from A, and the edge from A to B. Oh, it should be from S to, yeah, the edge from S to B here. It's not stretched now because this is too long. It's not stretched. Yeah. Okay. And the one from S to C is now kind of tight. Yeah. So basically no edge will be stretched. Okay. And every node will precisely be at the position of its distance from S. And you can also see that the shortest path, the green one here is the one that is not stretched, but it's kind of tight. It's not, how do you call it? Yeah, it's tight but not stretched. This is the green one. And you can see that shortest path will be using only the tight edges. Yeah. If you're gonna never use the non-tight one because it's kind of go in the, it's not going in the shortest way. Okay. So this is a kind of nice physical process that gives you a intuition of shortest path, what it is. That is, just have a network of nodes and then fix S and then hang the network on the wall, fix S and see where are the position of every node. That's the distance to S. Okay. Make sense? Okay. And actually this physical process actually can motivate the algorithm too. So the way that you think abstractly might be you imagine that you have the real line, start from 0 and 2, and 1 and 2 and 3 and 4, right? And if I denote d of v to be the position of vertices, and I start a node S at 0 and every one at infinite. Okay. And what I'm gonna do is like I kind of try to relax edge. In the previous slide, I just relax every edge simultaneously and see what happened, right? But like right now, every edge is kind of like a stretch because here is like at infinity. We're gonna try to relax edge. And what does it mean formally? To relax an edge UV, it would mean this. We're just gonna put the we're just gonna try to ensure that the edge UV is not stretched by decreasing the position of V. Okay. So what do I do? Like I take the position of V and try to decrease it by how much? Just look at the position of U, right? If U is here, and maybe like this edge, and let's say like this edge was super stretched. So I gonna, but maybe like the edge length is maybe 2, and maybe this is like at position I plus 1, I plus 2, and so on. So we're just gonna like decrease position of V to here. And now an edge is not stretched. At least this edge is not stretched. This is what it means to relax an edge. So when you see like the word relax an edge in Dijkstra, this is really what it means, like to relax the stretched edge so that it's not stretched anymore. Okay. And basically you start with this and you can basically ask, okay, what kind of relaxation can we do on each edge so that at the end of the day there is no stretched edge left. And once there are no stretched edge, then you are basically at the point where you get the distance of everyone, just like in the previous slide. Okay. And if you think about it, if you like with this intuition in your mind, and you look back into Bellman-Ford algorithm, Bellman-Ford algorithm really just do this. Like repeat the following for n-1 round. And it just, for each round, just go through each edge one by one and relax each edge with this rule. This is what happened in Bellman-Ford. And there are like m edges. You can just go relax each of them once and repeat for n rounds. So that's why the running time is mn. Okay, but this is kind of wasteful because you kind of relax every edge like n time. And basically the idea of Dijkstra is that there's gonna be like the clever order of how you choose to relax edges so that every edge is gonna be relaxed once. And because every edge is relaxed once, then the running time is linear. It's basically linear. When I use tilde here, I kind of hide some log factor, okay? Like it means maybe there is like a log n here. I will use this notation. Or polylog, log square or something. Okay, good. So that's like the intuition of Dijkstra. Yeah. So once there are no negative edge, then you can relax every edge once. Okay, and what's the algorithm again? Like it just start like what we do, right? Like put the position at s of to be 0, everyone at infinite. And now it's gonna like we're gonna do this. Just set like choose the kind of the finalized set to be like okay. Repeat until every node is finalized, and we just do this. Look at a node that is not finalized here, not finalized yet, and take the one that like has minimum estimate right now. Put this guy to your finalized set. And what we're gonna do is just look at edges incident to you, relax all those edges incident to you. So you're gonna decrease the estimate of like the guy that is incident to you, like decrease the estimate of V, and then repeat. Okay. So you can imagine what's going on. Right? We just like kind of keep relaxing edges, keep relaxing the stretch edges in some order. So you have seen and you are familiar with this. Actually, you learned it before, but today we're gonna just try to prove that this is correct formally. Yeah. Okay, so how to formalize this? Well, I'm just gonna need some concept. Okay, so F was the finalized set that we defined in the algorithm, and now like what we try to do is this. We will try to maintain this thing basically. That is, we try to make sure that our estimate D, the position of each node, or the estimate of the distance, is such that for every node that is finalized, then the estimate of that node is correct, is the correct distance. How about the one that is not finalized yet? The estimate of V is going to be something that is not quite distance, but is distance from S to V with respect to F. What do I mean by that? I mean, this is just the shortest length to go to V through F plus one more edge. That is, F is like a ball around F. F is like the ball around S, right? And we're just gonna say that like this V to S to V of with respect to F is just minimizing over every node in F, like this, maybe U, and take the distance from S to U plus one more edge from U to V. Okay. And the key claim is this. So you see that like this is something that could be bigger than the real distance. Like it's like it kind of restrict yourself to this kind of path where you go through the shortest path inside F and then take only one more edge. It doesn't look at all kind of paths, right? So distance with respect to F can be more than the real distance. Okay. But now, okay, everyone in F have like we're gonna make sure that everyone in finalized guy have the correct distance, but the guy that is not finalized is not done, maybe not done. But the key claim is this. I want to say that, okay, this is not quite the real distance, but at least for the guy that is not finalized, but it has minimum estimate among not finalized guy. Actually, this estimate here is already this one. The estimate here is already correct. That is, for the not finalized one, the distance with respect to F here from S to U is already the real distance. That's my claim. Is a claim understandable, the statement? Question about the statement. All right. So so basically, take the guy that is like kind of not finalized but closest, like but minimize the the estimate is minimized, then this is already like the estimate we have is already correct. Okay. So let's try to prove this. It's actually the key claim. So suppose that it's not the case, right? We're gonna show contradiction. So suppose that like this thing is actually strictly more than the real distance. Okay. If this is not equal, then it must be strictly greater than the real distance. Suppose that's the case. Then what does it mean? It means that like the shortest path from S to U, let's call it P, this shortest path must use at least 2 steps outside F. Right? Because if it can use just 1 step outside F to U, then this F here would be the real distance already. But here we said that, okay, this guy is strictly worse than the real distance. So the real distance, the real shortest path, must use at least 2 steps outside F. Clear? Yeah.
I guess I don't fully understand. So you're saying that the distance, so when you say the F set, the finalized set, it's 1 step outside of that finalized set to get to U. Why are we allowed to take that 1 step outside of the finalized set? Because I thought that U had to be contained within the finalized set for this to be true.
No. So like here U is outside the finalized set by definition. Like I said it, like look at U that is not finalized but has a minimum estimate. Now I claim that, okay, the guy that is not finalized yet, I have this estimate in, like I assume that I have this estimate for the guy that is not finalized. My claim is that this guy, U, not finalized but minimum estimate. This guy is already the same here. That's the claim. Is the statement clear to you?
Yeah, I think so.
Okay. And I'm just saying now that if let's try to prove this, that they are equal. Suppose not. Suppose for contradiction that is not the case. It means that this estimate for you is not the right distance yet. So it must be strictly greater than the real distance. And once, if it is the case, how can that ever happen? How can like this F from S to U is more than S to U, like this real distance from S to U? This is because this can happen only because, the shortest path from S to U kind of need to use more than 2 steps outside F, because like the definition of this F, distance F, is the shortest path that go to that node through F and just one edge, like 1 more step outside F. But this guy is first. So now it means that the real distance must use at least 2 steps outside.
Okay. The distance or distance function, are the length of the edges the same in this case, or not?
Not the same.
So what if I'm confused on like what if the distance to U, alright, like on the top where you have V to U where it's only 1 step, you know? Like
From V to U here?
up, like on the top of the screen.
Okay.
Like 1 step versus 2, because 1 step's at the top and 2 steps on the bottom, right?
Yeah.
What if the 1 step is expensive? Like they call like the 1 step.
It could be
cost.
expensive.
It could be expensive.
It could be expensive. That's why like this one
Yeah,
can be worse than this one.
that one can be worse than that one.
Yeah.
Yeah.
I'm just assume that like I maintain this invariant.
Okay.
If this is the case,
Yeah.
then I'm just gonna prove this right now. And later I'm just gonna prove that we really maintain this invariant.
Oh, okay.
Yeah.
Thank you.
Okay. So back to the proof. Suppose for contradiction, if this is greater than this, everyone agree that like the real shortest path to you must kind of take 2 steps outside F. So there must be like let V be the first guy outside F in this path. That one is not you. Okay. V is not you. And so I can write down like this. The distance from this is the distance from S to U is the same as it's gonna be like distance from S to V plus distance from V to U. And this is just like the property of shortest path, right? Like when you kind of look at the shortest path and take like a sub interval of shortest path, you can just sum them up. Okay. But I claim that this thing is just the same as this of S to V sub F. Why is that?
Because it's taking a path that only takes one edge outside of F.
Yeah, it's by the choice of V. It's the one that it use just 1 step outside F. So these are the same.
Yeah.
Good. All right. So far, what do we have? We have this. Okay. Now I'm going to try to derive contradiction. Okay. So I claim that this whole thing is actually at least F of SU. And if we can show this, then we are done. Right? Because like you get this guy is greater than the same guy. So something is wrong. Contradiction. Why is this the case? So I just gonna say that. Yeah. Basically, I claim that this one is greater than this, and this one is greater than this one. Why is this the case? Why, like, this F SV is at least this F SU?
Because how we defined it with U as the argument.
Exactly. U is the argument. U is the one that has minimum this F. That's our choice. So this one, U is the one that minimizes this F. So it must be like us, at most this F of V. How about this? Why this is like at least 0?
No negative edges.
Yeah, there is no negative edges here. That's the point. We need to use this fact at some point, right?
Yeah.
So we are done now. We get a contradiction. Okay. So among the one that is not finalized, the minimum estimate among not finalized guy actually have the real estimate, the correct estimate. Okay. Good. Question? Good. So
That would be the estimate.
so now we're gonna basically try to prove this loop invariant that we just said in the Dijkstra algorithm. Okay. So we have this pseudocode and we want to prove this invariant. First of all, suppose that this loop invariant holds throughout the whole algorithm. You can see that then it means that the algorithm is correct, because at the end of the day, everyone is finalized, and we're gonna return our estimate D, but the loop invariant said that everyone that is finalized have the real estimate distance. The distance estimate is correct. So this loop invariant is something that is useful to prove. Now let's try to prove it. Okay, so let's try to say that, okay, at least after the first loop, then the invariant hold. Both invariant hold. And you know that after the first loop, what do we have? We have that f is gonna be basically just s. Like we're just gonna finalize at one node, which is f. Okay. And you can also see that the invariant would be correct because the distance, like for s itself, the distance is actually 0. So this is correct for s. How about everyone that is not finalized? We basically just relax everyone incident to s. So like you have s and all of s neighbor. Now the like if v is neighbor of s, then now d of v would be exactly the length from s to v, the length of this edge from s to v, which is exactly which is like distance distance f from s to v, right? For every neighbor of v, you get this one. Everyone is not neighbor of v, it's infinite. So the second invariant holds as well. All right. So now both invariant holds in the first loop. Now the next goal is like, okay, we want to say that the invariant keep holding after each next loop. If this is the case, then at the end it's gonna be true. Like everyone is finalized and we are done. We get the correct. So now let's try to say that after next loop, like assuming that the invariant holds for every step up to now, and then the next loop, they like both invariant will hold still. Okay. So okay. So I claim that after the let's look at the next loop here, and let's say we run up to here. Now the finalized set grow. Why would the invariant 1 still hold? Yeah, Scott.
Because of the property we proved on the last slide.
Exactly.
Since we picked the argument and we just proved that that has to be the actual, or the dist f has to be the actual distance.
Yeah. Just from the last slide, the key claim that we proved, right? We take u to be the minimum finalized guy, and the estimate of u is already correct. So even if u is now added to finalized set, this would be correct one. So the invariant 1 is true by the key claim from the last slide. And the invariant, like the second invariant would be true as well because of the relaxation step. Why? So like for everyone that is not finalized, we need to update this f. How can this f change after we grow f by u? After we add u into the set f? This f can change only because of some path that go through u and take one step to v, right? And we do exactly that. Like we just update so that now the estimate of v can decrease according to like a distance that go through U and take one step to V. This is exactly what relaxation step does to make the invariant hold, the second invariant hold. Okay, so that means like both invariant holds through the next loop, and it's gonna keep holding until the end. And yeah, at the end we return D, and D is the real distance by invariant one, and we are done. That's like the formal proof. Yeah. Question about this? Okay, so now let's try to think about like how fast this algorithm is, right? And we're just gonna use priority queue or heap for implementing this one. And priority queue is just a data structure, it's like an API that have some function for you, and you can call each of the function that it provide. What function does it have? So priority queue, you're gonna basically maintain a set. And what can you do with this set? The first function that you can access it is to insert. So to insert x with key k to the queue. So add x to the queue with value of x equal k. Okay. And next, what you can do is also to delete min. That is to find the element that minimize the value or minimize the estimate d. Okay, so that just delete x from the queue and return it. Find the minimum guy, delete it, and return this x to you. Okay. What else can the heap do? It can decrease key. That is, look at any element with the value k, then you just decrease the value of this element to at most k. You can decrease the key. Okay, and you can see that with this data structure, it really it's kind of built to implement Dijkstra. Why? So what you do here, in the initialization, you just insert, for every node, insert it with the value ds or dv to the queue, right? And to implement this, just delete min. It's just gonna give you the guy that is with minimum estimate. Just delete min. And now what you do here, you can do just by decrease key. Okay. So priority queue will basically contains all the node that is not finalized, and you keep decreasing its key, and sometimes you take the minimum guy out. Okay. So we're gonna call insert n time here, and delete min n time, because that's the a number of loop we do. And decrease key, what do we do? How many times do we do in total? We call this basically sum over node, degree of the node, and that's OM. So that's the total operation that we call to the heap. Okay. And now it's just to finalize the running time. It's just about how fast you can implement each of these operations. Now we count how many times we call each operation. Now just count how to implement each operation fast, right? And there is a trivial way to implement priority queue, which is first way is just to use array, right? Just suppose we know that here we know that the maximum element there are just n element. So we just insert in one time, put it into that cell. Decrease key, just update that cell, that takes all one. For delete min, well, if it's array, you just now need to scan through the array. That takes n time. So there are n insert, m decrease key, and n delete min. So the total time, if you use array to implement heaps, then it takes this much time. But you can do better if instead just try to implement priority queue with better data structure like a balanced binary search tree. Then everything you can implement in log n time, right? You just store it in like a balanced tree. The depth is log n. Whatever you do is take log n time. And so like there are n plus m operation. So the total time is now m plus n times log n. So that's better. If the graph is not too dense, yeah, then it's better. And so today we now see like the correctness proof of Dijkstra with this running time. And later in class, like next week, we're gonna actually improve the running time to m plus n log n. We're gonna do this using a better heaps, like not just implement it using BS3, use something more clever. And to do that, to analyze this kind of heaps, you need to know more about amortized analysis. But that's for next week. Okay, so that's for Dijkstra. It's like a nice, really influential shortest path algorithm.